I'm here to talk about auto-instrumentation GPUs with eBPF, or sort of. My colleague Ananya is not able to make it this time, but he helped me prepare this presentation. So, anyways, to get started, we're going to talk a little bit about defining the problem space, what this is about, why I'm talking about this. We're going to go into the basics of GPU monitoring, and eventually we're going to see how we can supercharge that with some eBPF, whatever that eBPF is for those that don't know. All right, so why do we want to monitor GPUs? Well, and I say GPU here, I'm just pretty much speaking about NVIDIA at the moment, because that's the GPU everybody runs workloads like LLMs and AI workloads on. There's other ones, other players in the market, but NVIDIA is dominant. And as much as you want to, whatever, I don't know on which side of the spectrum you are, you believe that this AI bubble is just going to burst, it's never going to come back, and this is all nonsense, or you're one of those that believe there's going to be AGI very soon, and we're going to get overtaken by robot overlords and something. It doesn't really matter which way it ends up. What we've invented so far with these LLMs, my conviction is that there's a lot of useful stuff here. And even if there's a bubble burster and none of that actually really happens, we have 10 years of good stuff to come out of what we've come up with so far. So these workloads will permeate into the regular workloads your application developers are building. There's going to be more and more of this, and they're all going to run on specialized hardware because CPUs right now cannot deal with this kind of workloads efficiently. And they're very expensive. So when I was preparing this talk, I have a 3090 GPU on my desktop, which is really a kind of lower-end model. And I wanted to try out this Wave 100, which is the flagship, top-of-the-line NVIDIA chip. And Grafana told me it would take them 2 weeks to actually have the platform make one for me or allow me to use it in the cloud. And I was like, forget about that. I'm just going to go rent one out straight up in GCP on my private account. And when I wanted to reserve the instance in GCP, it told me it was 70,000 Canadian dollars a month to rent it out. So I was like, no way. I'm going to wait the 2 weeks. So because of this, we want to make sure that we know when these things are not working well, or we need to monitor them for failures and stuff like that. So how do teams typically use these? And probably somebody here maybe even knows more about this than me. They run these more in production, but typically there's various teams submitting some LLM jobs. Some of them may do training, even if it's not full-scale training from scratch. Maybe they're just simply fine-tuning an existing model. Somebody's running inference or producing answers for LLMs. That goes through various schedulers that push them to various of these graphic cards and GPUs to produce the actual answers. Now, what we don't want to happen is the scheduler pushes all the data to some of these GPUs, but not to the others. And some of them are overloaded, and your workloads are suffering. So we need to know when this is happening, right? And why is this so important? Especially because this is a report about what happens. 30% of the failures, according to Meta, on these kind of workloads are because of hardware failures. So they overheat, cooling is inefficient, whatever it is, causes this hardware failure, so we need to know when these things happen. All right. So how do we go about monitoring these GPUs to find out how well they're performing, what's going on, and so on? The first step in all monitoring, NVIDIA's tool, is sort of similar if you ever had like a Prometheus node exporter, when it kind of captures memory, CPU utilization, like I/O, that kind of stuff. You have this DCGM exporter from NVIDIA, which kind of captures all this low-level data about the GPU itself, which is kind of useful. So you get GPU utilization, power draw, and so on. So I, for example, use this GPU exporter on my 3090 on my desktop, ran Qwen3 from Alibaba as a workload, and you can see kind of like efficiently extracted this data. I was able to put it in Prometheus and build in 5 minutes some Grafana dashboards, which is kind of neat. So you can see over here at the top corner there, my GPU utilization, I was getting about maybe maximum 65%. I'm trying to push this Qwen model as much as I can, but I wasn't able to get more than 65% of my GPU to be used. For whatever reason, I don't know. If you've ever done any of the traditional CPU monitoring, this is kind of typical, right? You know that maybe you have 40% GPU utilization, but you can't push your application more because maybe it's I/O bound. There's something else that's actually causing it to not be able to leverage all the resources you have available in the system. But the GPU doesn't touch any databases. There's no I/O. What's going on here, right? So for deeper analysis, what NVIDIA provides is this insights, whatever, system, which is kind of a really good profiler. It really lets you go really deep into the GPU mechanics. Like, I don't know, like on CPUs, we had something like Intel VTune at the time, and it really goes deep into CPU counters and all what's going on with the CPU, so you can easily find out, maybe if you know, if you're like a low-level guy, a practitioner, you know this space, you can figure it out. Same with NVIDIA, you have this low-level tool that can visualize what's happening in the GPU, and if you know what you're doing, you can find out perhaps what's going on. However, there's a couple of problems with this. Like if you remember my initial slide, I had that scheduler and had all these teams pushing work to the GPU. So when I'm profiling, what am I profiling? Which model? Right? This is dynamic, this changes. It's no longer just my GPU on my desktop that I'm profiling, trying to extract the most out of this workload and optimize. A lot of stuff is going on. And the main challenges with CPU profiling is that first there's an overhead. Then I can't just scale this across my whole platform. And how do I do this continuously to find out what's going on? And how do I tie that to the CPU workload or even to the pod that's actually causing this workload to happen on my GPU? So it's not ideal. It's not what we're used to in today's days and age of how CPU profiling works. When you put in a profiler across all your farm, extract that information, ship it somewhere, and review it, and do diffs, and so on, and tie it back to exact workload and application. All right, so what makes this GPU so special? I'm going to go in a little bit about the architecture that makes them unique and difficult or tricky to understand and tie to the regular sort of workloads that we're used to seeing in our application stacks. So first of all, it's actually a supercomputer on your actual hardware. Like, it contains this tens of thousands of these little tiny, tiny cores that you have to ship data from your CPU into their memory, and it has also its own memory, and you tell it to run this massively parallel work. And after it's done, you tell it to run some other massively parallel work until it's finished whatever you've told it to do. Now, the way it's organized is sort of even more complicated. So each one of these, they're called blocks, contains a limited number of threads, usually 1024, 1K, and each thread maps into a single of these cores on the GPU, which are mostly good for doing numerical computation, but there's many of them. And now the trick is, to use it efficiently, is to bundle all these blocks into grids, they call them. And the bigger the grid, the more efficiently you're going to use the GPU, which is kind of cool. But at the same time, what you're running on these cores is these tiny, tiny kernels, they call them. So typically like a matrix computation or something like that, very numerical operations. And how does this tie to LLMs? Well, if we break down what typically happens on the GPU when you ask Llama from Meta to do something. And what that means, do something, is you put in some text and it's going to predict the next token or the next text to show you the answer, essentially. And each one of those steps runs this particular pipeline of operations. Each one of those are very simple, like matrix multiplications, normalization, and things like that, eventually produces an answer. So each one of these are separate kernels that typically get launched. And these kernels now, or what happens, you launch the kernel, you wait until those parallel operations finish, you kick off the next, and so on. Now, you may see the problem here, but let's go dive into more details. So, it's all good, and how does this whole eBPF that I want to talk about here play into this whole thing? What is this about? All right, so eBPF is technology that existed for a while. It stands for actually Berkeley Packet Filter, but it doesn't mean that anymore. It was originally developed so people can filter packets on Linux kernels with different algorithms and so on. So they created a system where you can kind of extend the kernel with different programs, and you can attach it to various parts of the kernel in a safe way. So think of it as like kernel modules, but without the downsides. It will never destabilize your system. You can turn them on at any point in time. You can take them off, and there will be never disruption in your workload. The good thing about them is that these eBPF programs, you can launch them at any point in time, which means you could run your GPU workload, say for example, for days, right? And then you decide to profile or get more information about it. You can plug this in, and you can take it out when you're done. And you can do it periodically, you can do whatever. You don't have to restart the work or anything like that. It's zero instrumentation, you don't have to touch it, and it's framework agnostic. What I'm going to show you today is that it doesn't matter if I'm running Qwen or Llama or whatever, VLLM or SGLand or PyTorch, it all boils down to the same thing. So I worked for the last 3 years on this product, which started as Grafana Bela. It was Grafana proprietary product, not proprietary in the sense that we owned it. It was open source from the get-go, but it was owned by Grafana. We in May donated it to OpenTelemetry, so now it's CNCF project. It's called OpenTelemetry eBPF Instrumentation. It does instrument many things. We can do application observability, network observability, but what's interesting about this talk here is that it does have these hooks into the CUDA library, which all this LLMs and AI software uses to actually submit these kernels into the GPU. So we instrument stuff like CUDA launch kernel, CUDA memcpi, those kind of things. So the component itself has a user space component, which takes those low-level data points and turns them into meaningful metrics that you can then put in, say, Prometheus over there. And once you put them as metrics there, you can plot them, graph them, create SLAs on top of them, create alerts, whatever you like. It's just a standard monitoring database at that point. Now, what's another interesting thing here is that that user space component can also talk to Kubernetes API. So we last year presented at this very conference a talk from my colleague, Mark Tuduri, presented called From PIDs to Pods. He talked about how we correlate process information, the low-level kernel stuff, to a pod. And using that technology, we can then, all these metrics that come from the GPU, tie it to a specific pod in a Kubernetes cluster to know where this workload came from and what was it about, which is kind of useful. To at least know the application that's causing the GPU load or whatever it's doing. All right, so that's pretty cool. So let's see what happened. I'm back to my local desktop for now, and I'm running this 3090 where I did before. So then, using this tool, I was able to get a little bit more information. And so at the top, I actually used Prometheus SDK to extract the latency that I'm getting. This is the P95 latency of my queries, so about 48 milliseconds per query request. I'm plotting that maximum CPU there, 64%, and I got a bunch of data over here about kernel launches for Qwen 3, grid sizes, memory copies, different kinds. So like copies from device to the from the host to the device, between device to device, and so on. And now you're wondering here, what the hell is this? How does this even help me? Right? So yeah, you talked about this GPU, and then you got this additional kernel data, whatever, but what does this ever mean? Is this good or bad? I don't know. So I'm going to show you through an example how to interpret this data and what this actually means and how it can help you actually understand if this is good or bad. Fortunately for us, two things happened this year, earlier. In May, this project was announced by Stanford called Thunder Kittens. And then later on, about a month later, in June, there was a project announced by Carnegie Mellon, CMU, when they talked a project called Mirage. So what they talk about is like, they take these kernels and they all convert them into something called a mega kernel. So they take these tiny, tiny operations, if you remember my Llama pipeline, that took one by one. So they figure out what's going on inside, break them apart, and combine them into one giant program. So pretty cool projects, and let's see what that actually does. So this is my original story. I can't push my 3090 beyond 65% here. It's held up by something. I don't know what it is. I took the Mirage project, and this is what happened. I don't know if you noticed the difference. Just watch the top. So it used to be 48 milliseconds to finish my request P95. That went to 11 milliseconds. 4x improvement on the PyTorch straight out of like Hugging Face. I downloaded the original Qwen 3, produced by Alibaba, optimized it with Mirage, and this is what I got at the end. And the important stuff to notice is that if you see the kernel counts are around in the hundreds, tiny, tiny kernels being launched, and that comes into like 100x magnitude reduction by running this kernel. At the same time, what used to be majority of the memory copies were device to host. So I'm constantly copying data from my CPU memory to the GPU memory. Now that's completely eliminated, almost nothing. Most of the memory copies are GPU to GPU, which is what we want to see. We don't want the data to be coming back and forth. And at the same time, probably the most important part is that the grid size, which was maybe on average around 800, jumped up to around over 3,000. And so now we're efficiently using the GPU. I was able to get 100% of utilization there, and my workload improvement of 4x. Did nothing, pretty much. I didn't have to buy new GPUs. I was running 4 times faster. Now you're wondering, okay, well, this was your GPU that's sitting over there. What happened to the A100 that you wanted to rent for 70,000 Canadian dollars? So this is my A100 that we ran the same experiment, but to be fair, we wanted to try a completely different framework over here. We didn't want to run Qwen 3. We say this is framework agnostic. We wanted to run Llama, and we ran it with VLLM, which is a framework. There's a couple of them popular, SGLand, PyTorch, Llama, VLLM. So over here, we see Llama is actually slightly different, but again, the same problem appears. So I bought this for $70,000 a month. I'm renting it. I'm only able to use it 48%. It's not very good return on investment, if you ask me. And while they don't have hundreds of these kernel launches, it's in tens. But if you see from before, we still have the memory host to device copies happening, not as much as before with Qwen 3, but at the same time, the kernel grid size is pathetic. It's in the hundreds. Different engineers worked on different models. They optimized differently, which is why we're seeing less kernels, but grid sizes are really bad. Now we took Thunder Kittens, and we optimized this model, and this is what happened. So I got half the latency. So we sped up this model twice, like 2x, taking the VLLM Llama from Meta. And if you look what's happening, the kernel launches dropped by 10x. We, again, eliminated almost completely device to host copies. And at the same time, the grid sizes went to the high thousands rather than whatever was like hundreds. So when you have an LM workload and you can't push it high enough, these metrics that we extract show the real reason why either you're maybe not supplying enough data and you're not supplying enough requests, which is maybe why your GPU utilization is not where it's supposed to be. You're not fully utilizing it. But it also could be the design of the model itself is preventing you from using that no matter what you do. And these metrics, the grid size in particular, the number of kernels launched, and how much memory is being copied from the host, from the CPU to the GPU, is what actually quantifies as a measurable indicator that this is not running efficiently. This is what we want to see, essentially. And so to summarize, GPU instrumentation is very important. And even if it's not important today, it's going to become important very soon as people build more and more LLM workloads into the infrastructure of the applications you're monitoring and day to day. It's like in Canada, I have to put a hockey reference. It's not where the puck is, it's where it's going. So this is going to become a lot more important. eBPF can get us a little bit more insights than what we have today from the standard GPU metrics, like GPU utilization, memory on the GPU, and so on, because we like to find out why our GPU is not able to utilize its resources. And this last statement here is a new blog post that just came out a couple of days ago from the same Thunder Kittens guys. It said, we bought the whole GPU, we damn use the whole GPU. So there's a lot of optimization and low-hanging fruit that can be done, even from the models coming out from the major vendors, which we believe they should be doing the best they can and really optimize this. But as we can see here, with third-party tools by research organizations, we can optimize this to much better outcomes. That's it. Thank you.